Hi and Assalamualaikum. Today our group will present our project titled Design of Low Pass Filter and Band Pass Filter using insertion loss method. This project was carried out for the BERT3414 RF Technique and Microwave course. In this presentation, we will explain the design process, simulation result, and performance comparison of the filter. So let's begin. Before we start, let me introduce our group members. Me, Nurulain binti Hisham. Next, Mohd Razmer Ar-Ridzwan bin Mohd Rosli. And last, Mohd Faiz Adni bin Mohd Yusri. We worked together to complete this project, including the design calculation, ADS simulation, analysis, and presentation preparation. Now, I will continue with the introduction of the project. So, I will start with introduction. This project is about the design of low-pass filter and band-pass filter using the insertion loss method. RF and microwave filter are very important in communication system such as mobile communication, satellite system, radar, WLAN, IoT and 5G network. The main function of a filter is to remove unwanted frequency and improve signal quality. In this project, we focus on two filter types, which are the Chebyshev low pass filter and the Butterworth band pass filter. Next, the objective of the project are: first, to design a first-order Chebyshev low-pass filter using the insertion loss method. Second, to convert the lump element low-pass filter into a distributed low-pass filter using Ricard transformation and Kuroda's identities. Third, to design a fourth-order Butterworth bandpass filter. Finally, all designs are simulated in ADS and the results are compared with the design specification. This slide shows the design specification of the low-pass filter. We use a Chebyshev equal ripple response with a cut-off frequency of 2.8 GHz. The stop band frequency is 7.6 GHz with a ripple value of 3 dB. The minimum attenuation required is 50 dB and the source impedance is 50 ohms. These specifications are used as the target during the filter design process.
Next, I will explain the design procedure of the low-pass filter. First, we determine the filter order based on the given specifications. After that, the Chebyshev prototype values were obtained from the standard table. Then, the inductor and capacitor values were calculated and used to build the lumped element LPF in ADS. The circuit was simulated using S-parameter analysis to verify the filter performance. After obtaining the lumped filter result, Ricard transformation and Kuroda's identities were applied to convert the circuit into a distributed implementation. Finally, the distributed filter was simulated and verified to ensure that it met the required specification. This slide shows the lumped element low-pass filter design. The filter was implemented using two inductors and two capacitors arranged in a ladder network configuration. The component values were calculated using the insertion loss method and then implemented in ADS. The purpose of this design is to provide the initial verification of the filter before converting it into a distributed structure. This step helps us confirm that the calculated component value produce the expected low-pass response. After verifying the lumped filter design, the circuit was converted into a distributed low-pass filter. Ricard transformation was used to replace the lumped inductors and capacitors with transmission line. Then Kuroda identities were applied to convert series stub into shunt stub and create a practical open stub structure. This distributed implementation is more suitable for microwave frequency application because it reduces parasitic effect and can be fabricated more easily on a printed circuit board. This slide compares the performance of the lumped and the distributed low-pass filters. For the lumped LPF, the cut-off frequency was approximately 2.59 GHz and the attenuation was 55.36 dB. Although the filter worked correctly, it did not achieve the required attenuation of 50 dB. For the distributed LPF, the cut-off frequency was approximately 2.8 GHz and the attenuation reached 50.95 dB. This result satisfies the project requirements. Therefore, we can conclude that the distributed LPF performance better than the lumped LPF and is more suitable for practical microwave applications.
Next, we design a fourth order Butterworth bandpass filter. The target specification are a center frequency of 2.8 GHz, a bandwidth of 310 MHz, and a standard 50 ohm impedance. As shown in the ADS schematic, we implemented a lump element circuit by using alternating series and parallel LC resonator to isolate our target band. The component value were calculated and optimized, starting from L1 at 19.65 nanohenry down to L4 at 0.411 nanohenry. Along with their respective capacitor, the setup ensure a maximal flat bandpass response. Looking at the simulation result, the S parameter plot confirmed that the filter performed excellently. Marker 1 show the center frequency is exactly at 2.8 GHz. Marker 2 and 3 identify the lower and upper negative 3 dB cutoff frequency at 2.651 GHz and 2.962 GHz respectively. This result is an actual bandwidth of 311 MHz compared to our specification. The bandwidth error is only 1 MHz. This minimal error proves that our design successfully achieved all performance criteria.
This slide compares the simulation result with the design specification. For the lump low-pass filter, the cut-off frequency is 2.59 GHz and the attenuation is 45.36 dB. This does not fully meet the required specification. For the distributed low-pass filter, the cut-off frequency is 2.8 GHz and the attenuation is 50.95 dB, which meets the design target. Therefore, the distributed LPF performs better and is more suitable for microwave application. The bandpass filter also achieved the target center frequency and bandwidth successfully.
To conclude, all project objectives were successfully achieved. The distributed low-pass filter meet its requirement with a 2.8 GHz cut-off frequency and 50.95 dB attenuation. Meanwhile, the Butterworth bandpass filter perfectly hit the 2.8 GHz center frequency with a high accurate 311 MHz bandwidth. Both designs were fully verified via ADS simulation and are ready for practical microwave application. That's all from us. Thank you.